Hi, we're going to start looking at travelling waves, that's waves that move from one place to another, with a brief introduction using the idea of water waves, because everyone is familiar, to a certain extent at least, to waves in water. So that's our idea. This is going to be a three-part introduction, try and keep each part quite short. So there's a picture of a water wave, something, a droplet of water, whatever, has disturbed the water in the middle, giving it an up and down motion, an oscillation, and that oscillation spreads out. It propagates. Propagation. All of this just means moving through or spreading out. And the other key point of the wave here, and this is true for all travelling or progressive waves, is that they involve a transfer of energy. Energy is moved from one place to another. Quick introduction to some vocabulary. So on the right hand side here you see this droplet and you see these concentric rings. And these concentric rings represent the crests and troughs of a wave and spreading out the energy from one place to another. Here in this cross-sectional view you see what we mean by a crest, which is sort of a peak or top of a wave, and a trough, which is the lowest point of a wave. And both of these are displaced from the what is labelled here as the still water level, which would be the equilibrium position. This diagram has wave height, which is from the trough to the crest. We more commonly refer to amplitude, measured from the equilibrium position, and it has wavelength, which you can measure from crest to crest or trough to trough or any 2 points in phase, although we don't use an L, we would use the Greek letter lambda. So all waves, we know they're waves. Well, one of the reasons we know why something is a wave is because it displays basic wave phenomena. And the four basic wave phenomena that we are expected to know and be able to explain are reflection, refraction, diffraction, and interference/superposition. Okay, so reflection you should be fairly familiar with. When one thing reflects, it bounces off, and that's what the waves are doing in this case. So there's a wave coming in here and then reflecting out here. This diagram shows it better. The wave that comes in we call the incident wave, which is shown in red on this diagram. So this is sort of looking down from above, maybe water hitting a shoreline. So the incident waves come in and then they reflect off as a reflected wave. And if you take a straight line here, which we would call normal, then this angle of incidence here would equal the angle of reflection. We'll look at that in more detail, as we'll look at all of these in more detail in a later topic or subtopic. Refraction. Now, refraction isn't as familiar as reflection. Refraction is bending of waves. Waves bend, they refract, and they do so for one reason. They do so because their velocity changes. With water wave, what determines the velocity is generally the depth of the water. So, as a water wave travels from deep water to shallow water, it slows down. You'll notice that the wavelength gets shorter, okay, the distance between the crests. Where the boundary there is not exactly in line with the waves, because one part of the wave will enter this shallower water first, the net effect, the overall effect, is to bend the wave. It bends the wave towards the shallower water angle. You can see that actually in effect from this sort of Google Maps image. Water waves are coming in fairly steadily here, but as they approach the coast, they bend towards the shoreline. Here's another diagram showing the same thing. Water waves, as it gets shallower, as the depth changes, the velocity changes, and it ends up bending towards the shore. Refraction. Superposition, interference, basically the same thing. These are a series of ring ripple patterns produced by falling water, by rain. You'll notice how the different rings sort of act on top of each other, as you can see here. Okay, so they spread out and they move past and through and on top of each other. This diagram here is A is a source of a wave and B is a similar source of a wave. And you'll see both of the crests and troughs moving out and through and past each other without bouncing off or doing anything like that. The next and final wave phenomena that I wanted to illustrate using water waves is simple diffraction. When a wave passes through a boundary, a gap, or just an edge will do, it diffracts. It spreads out in a sort of circular pattern most of the time. So waves here approaching from the, I think this is going to be the seaward side or the lake side, and this is the an inlet or a cove or a river or something. And there's a barrier here, an artificial barrier, which leaves a bit of a gap. And notice how these waves are nicely diffracting on the other side of that gap. They're spreading out as a circle. As I said before, we'll look at the reasons for this in a later sub-lecture. And here's a satellite view showing the same thing. Water waves here pass between these two islands which form a gap, and you get this very nice diffraction pattern coming off here. Okay, you get a similar diffraction pattern at the edge here, and here we can see interference, superposition, both of them one on top of the other. And presumably over here you can see some refraction as it approaches the shoreline. So all the different wave effects pretty much illustrated there for your pleasure. So we've introduced the concept of waves using water waves as an example. Thank you very, very much.